Continuing theorems on open sets in metric spaces. In a metric space, the union of arbitrary collection of open sets is open. Union of arbitrary collection of open sets is open. First, understand what is arbitrary collection is. Arbitrary collection means a random collection, randomly selected sets. Before we understand this, first understand finite collection. In finite collection, we write it's a collection of Gi. I belongs to natural number. I is running from 1 to n, like G1, G2, G3 and Gn. In randomly chosen, there is no pattern to be followed. We randomly select. Suppose I have taken G1 and then I have taken G15 and then G20, G100, means there is no pattern in the index. So what I'll do is I'll write the indices in the index set. That reverse triangle symbol is 1, 15, 20 is an index set, and the collection is represented as G lambda. Lambda belongs to index set. So this is arbitrary collection. Now come to the theorem. Union of arbitrary collection I have to prove of open sets is open. So first, in a metric space XD, let G lambda belongs to index set, be an arbitrary collection of open sets. These all are randomly selected sets and these are open sets. And let G be the union of such sets which are open. We need to prove G is open set here. So if suppose the collection I have chosen is of empty classes, if the whole collection is an empty class, then G, which is union of these sets, will also be empty, and so G will be open trivially. There is nothing to prove. Now suppose the collection is non-empty, and since G is union of these sets, then G is also non-empty. And suppose X is any element of G. For open set, I need to prove the sphere centered on X is existing in G. SXR is a subset of G. This is our aim. And since X belongs to G and G is a union of G lambdas, open sets, so X must be belonging in some set. X belongs to G lambda for some lambda. See, G is a union of open sets, so G will be kind of this. And I need to prove this, that sphere centered on X is contained in G. If X is belongings to G, X must be lying in one of these open set. It can be more than one also, but at least in one set X will be belonging. And since each of these sets are open, so sphere centered at X must be contained in that particular set in which X is belonging. SXR is a subset of G lambda for some lambda. And since G is union, so G lambda is a subset of G, so sphere goes into G automatically. And by this we say I have taken any element in G and G became neighborhood of this, so G is neighborhood of each of its points and hence G is open. This proves the result. Now the next result is based on intersection, and for intersection we need finite collection. In a metric space XD, the intersection of finite collection of open sets is open. For intersection we need finite collection. For union we can have arbitrary collection. So intersection of finite collection I have just discussed in previous result. Let XD be a metric space and let Gi, I belongs to natural number 1 to n, be a finite collection of open sets in X. And now let G be the intersection of this collection, Gi, I running from 1 to n. We need to prove G is open. In a similar way, if intersection does not contain anything and G, or you can say each Gi is empty, then G obviously will be empty. and being empty set it will be open trivially. So we need to consider that G is non-empty first to move further in the result. Let us assume the collection is non-empty and G is non-empty, intersection is non-empty, and let X be any element of G. So we need to prove the same result, SXR must be subset of G. To understand n collection, it is difficult to assume practically the n sets, so I am explaining the result in two sets. Suppose G1 and G2 are two open sets and X lying in the intersection. So X lying in the intersection means X lies in both the sets, right? And both the sets are open. So I'll be getting sphere centered at X in both the sets as subset of one sphere. I'll be getting with some radius as subset of G1, another sphere I'll be getting as a subset of G2. And similarly, now I'm discussing for n sets. Let X belongs to G means X goes to the intersection part because G is intersection, and since X is belonging to Gi intersection means X belongs to each and every Gi, and since every Gi is an open set, so in every set I'll be getting sphere centered on X with some radius contained in that particular set. Likewise in 2 I'll be getting SXR1 subset of G1, SXR2 subset of G2, and I'll be considering the minimum of the radii so that I can get the same sphere in both the sets. So I'll be considering the minimum, R be the minimum of R1 and R2. See, this is not part of the theorem. This is just I'm explaining for two sets. So SXRI is a subset of Gi. Suppose SXR1 is a subset of G1, SXR2 is a subset of G2, likewise. So we'll be choosing the minimum radii so that one sphere is contained in each and every Gi. So SXR subset of SXRI, I running from 1 to n, and each SXRI is a subset of Gi. So SXR will also be the subset of Gi, and then intersection part, and intersection will be G. So by this I have taken X as an element of G. Now G is becoming neighborhood of X and X was arbitrarily chosen. So G is neighborhood of each of its points and hence G is open. See, this was finite collection of intersection of open sets is open. Now the question arises, does the intersection of infinite collection of open set will also be open? Infinite number of open sets is also open. Justify your answer by an example. So for this is not true. This is not true always. I mean, it may be true, but it's not true always. So we need to find one such example in which this result is not true. So the intersection of infinite number of open sets need not to be open. For this we'll be considering one example. You need to remember this particular example, which is a case where infinite collection of open sets intersection is not open. So consider the collection as open interval minus 1 by n, n is any natural number of open sets. Since every open interval is an open set, that's why this is collection of open sets. So this is a kind of collection. G1 is minus 1 to 1, G2 is minus half to half, G3 is minus 1 by 3 to 1 by 3, and so on. This is infinite collection because natural number will not end, so this collection will not end. Infinite collection of open sets. And understand this on real number line. Minus 1 to 1 is a first set, minus half to half is another set, minus 1 by 3 to 1 by 3 is another set. Likewise, the series is contracting towards 0. So 0 is a particular number which will be present in each and every set, G1, G2, Gn up to last. So this is a metric space, considering R be the metric space with usual metric dxy as mod of x minus y, because we are discussing everything on real line. So intersection will be containing one element, that is 0. So it's a singleton set. And we already know that a finite set can never be an open set. It is not neighborhood of any of its points. This is a finite set. It contains only one element. So we won't be getting any open interval which will be contained in this set. Minus r to r open interval is not contained in 0. We won't be getting any such r. So this set is not open, hence the result. Next theorem. In a metric space, if A is a subset of B, then A naught is also subset of B naught. First understand this. A naught means interior of set A. Interior set means collection of interior points of that particular set. Also understand with diagram, A is contained in B. So A interior, which is just the A leaving the boundary points, and B interior is the set leaving the boundary points of B. Obviously A naught is under a B naught. Diagrammatically it's very clear. So how to write mathematically? Let XD be a metric space such that A is subset of B, where A and B are also subsets of X. Now we'll be taking element in A naught. When we need to prove one set is subset of another, we take one element of the set and prove it into the other. So let X belongs to A naught by definition means X is an interior point of A, and by interior point means the sphere centered at that particular element is contained in A. SXR is a subset of A, but A is subset of B given. So combining these two, SXR subset of B, which internally means X is an interior point of B, X belongs to B naught. Hence we have chosen element from A naught and it's lying in B naught. That simply means A naught is a subset of B naught.